Dear students, in this module on crystallography and mineralogy, we have been discussing various minerals, and you can look at some beautiful minerals here. In this sequence, we are talking about mainly the minerals which are present on the surface of earth or near to the surface of earth. Most of these minerals are formed of silicon and oxygen as essential constituents. As you know, oxygen is the most abundant element, followed by silicon. Therefore, the silicate constitute an important part of these earth material. Now, these are organized as silicon oxygen tetrahedra, and based on the way these tetrahedra are linked through oxygens, there are 6 classes of these silicon structures, in which all the minerals of the earth can be classified. Today, we are going to talk about one such class of minerals, and from amongst that one such mineral, that is the feldspar. Feldspar itself represents a group of mineral, but more of that I will come to that later. The feldspar constitute a part of tektosilicates. Now, tektosilicate is the kind of silicon tetrahedra structure where all the oxygens, corner oxygens of the tetrahedra are shared by other tetrahedra. Now, this leads to a typical silicon is to oxygen ratio of 1:2. Now, in this structure, if there is a tetrahedra structure in which silicon is to oxygen ratio is 1:2 and there is no replacement of silicon, then the formula, chemical formula of the mineral will be SiO2, which is what is represented by a common mineral, that is quartz. However, if silicon is partially replaced by some other cation with a different charge, commonly aluminum, then there have to be other associated substitutions at different sites to balance this charge. The charge difference between silicon and aluminum is 1, wherein the silicon is 4 positive charge and aluminum is 3 positive charge. If the silicon and oxygen bond is without any strain, then oxygen silicon oxygen bond angle is 140 degree. However, if this is not so, that is, if there are other cations which change this bond angle, then this bond angle can vary between 120 to 180 degrees. So, significantly large range. Similarly, the silicon is to oxygen length, bond length can also vary between 1.34 to over 1.6 angstrom, depending upon whether the oxygen is stretched or not. There is also a significant contribution of the environment in which these minerals form, and again we will see an influence of that influences the structure of the mineral also, the symmetry of the mineral also. For example, just to illustrate that if aluminum is replacing silicon and there are more than one type of silicon sites in which aluminum can replace, then at higher temperatures the distinction between these sites is blurred or they appear similar, whereas at lower temperature this distinction is maintained. So, this is called as order and disorder. At high temperature the site distinctions are not distinguishable and they are called as disordered, whereas at lower temperatures these are ordered. Okay, we are back in classroom and we are going to talk about feldspars. The general formula of feldspars is MT4O8, which means that there are 5 cations which are represented here by T and 1 cation M. So, 4 plus 1 5 cations for 8 oxygens. Now, in this T represents the tetrahedral site and M represents a site which has coordination larger than the tetrahedral site. In T site, we commonly have Si and aluminum, silicon and aluminum, whereas in M site there are large number of cations which are possible, which include sodium, potassium, calcium, rubidium, strontium and barium. So, this means that this chemistry can make several types of feldspars possible. Now, it is very interesting to note that both silicon and aluminum can be there in the tetrahedral site, and commonly there is about 25% aluminum in tetrahedral site on an average and 50% silicon. However, this is very strongly controlled in the way in which the feldspar forms. For example, if we look at this feldspar, a potassium feldspar, in this the high temperature variant of this feldspar contains on an average the randomly distributed 25%, means that 25% can be there, aluminum can be there on any of these tetrahedral sites, and on an average 50% silicon. If this same feldspars cools down to a lower temperature, then the distribution of aluminum will become restricted to some of the tetrahedral sites, and this is the phenomena of order and disorder. We will talk more about this later. So, this is the potassium feldspar, which can be there in several ways or several forms. The high temperature potassium feldspar is cyanidine, which because of higher disorder in the T site or tetrahedral site has monoclinic crystal structure. And it is very interesting to see how this monoclinic structure distorts at lower temperature to a triclinic structure. For this, now let us look at the arrangement of the tetrahedron, the way they are arranged and the way these tetrahedral sites are present in a structure, and how the larger cations are accommodated in non-tetrahedral sites. For understanding different types of feldspar, let us look at a figure now. Since there are 3 main end members of feldspar series, so we will look at a diagram where the epiphase is represented by potassium feldspar, one side is represented by the sodium feldspar, and the other side of the triangle is represented by the calcium feldspar. If we look at this division, this represents 3 major groups. Within this, the feldspars which are individually present with their distinct structure include cyanidine, orthoclase and microcline amongst the potassium feldspars, whereas the sodium feldspar is Elbaite dominantly, and the calcium end member feldspar is known as anorthite. There is complete solid solution, that is exchange of potassium and sodium in this fashion, and also there is a complete solid solution between sodium and calcium in this fashion. Within this triangle, the cations exchange can produce different types of feldspar. When we look at the sodium and the calcium feldspars, the various divisions are at 10 mole percent it is called Elbaite, 10 to 30 mole percent it is known as Oligoclase, 30 to 50 mole percent it is known as andesine, and 50 to 70 mole percent it is known as labradorite, and 70 to 90 it is known as bitumenite. From 90 to 100 the feldspar is known as anorthite. So, these are the major names or major divisions of the feldspar. Besides this, in some of the alkali feldspars there is a significant component of barium, and if that is present then that is known as the barium feldspar is known as Celsian. These are the major varieties of feldspars. As the temperature dependent substitution is represented by this area which I have shaded now. Amongst the potassium feldspars, the sanidine and the orthoclase represent a disordered tetrahedral site, which means that they are monoclinic, and I will explain the structure just now, and the collapsed structure or a triclinic or lower symmetry structure is known as microcline. So, to understand how this structure is described, we will look at another figure. When we look at the structure, in the first smaller figure we see 4 tetrahedron. All the apical and the basal oxygens are shared. Now, these 4 tetrahedron have arranged in such a manner that their apices are pointed alternately up and down. We look at the second part of this figure and we see now these 4 tetrahedron are arranged in some sort of rings, producing oval areas in between them. When we look at that oval area, you see that there is a line drawn vertically and the plane is marked as 0, 1, 0. So, that plane actually divides this structure into mirror planes, that is on 2 sides of this line 0, 1, 0, which means the plane containing A and C axis divides this as a mirror plane. Perpendicular to this is the B axis, which represents the two-fold axis symmetry or dyad axis. So, that is along the B axis. Now, this symmetry will hold only if the tetrahedron behave as shown in this diagram. However, if it is a lower symmetry structure, the tetrahedron, the mirror plane vanishes and it reverts to a triclinic symmetry. So, for higher temperature feldspar we have a monoclinic symmetry, for a lower temperature feldspars we have a triclinic symmetry. These 4 tetrahedral sites in higher symmetry are represented as 2 sites T1, T2, but in the lower forms they represent 4 tetrahedral sites T1, T2, T3 and T4. So, as you can see, the structure is beautifully controlled by the way in which the tetrahedra are arranged. We see this very beautifully illustrated in the 2 figures of high sanidine and high Elbaite. In the first figure, we see potassium surrounded by oxygen atoms. Now, all those, there are numbers written there. The numbers represent the OK bond distances and they are written in angstrom units. The first part of the figure, if you see, the two axes on the sides mark an angle of 90° between them, indicating this to be a monoclinic symmetry. Whereas, the second part of this figure, where potassium is replaced by sodium, you see that the angle is 93.4°, meaning that the orthogonal relationship is changed. Now, in case of sodium, if you observe the structure, the way the oxygens are distributed around is different. So, the sanidine structure represents the space group C2 by M, that is a two-fold axis and a mirror plane perpendicular to that, whereas the high Elbaite structure is a triclinic structure, as very well illustrated in this figure. So, when we look at the alkali feldspars, we see that there are range of alkali feldspars present, and in which significant amount of substitution can take place amongst different end members. Since I mentioned solid solutions in alkali feldspars, there are three distinct series of alkali feldspars which are present and which have different crystallographic properties. The first amongst these is high sanidine, high Elbaite, which to some extent I described just now. Now, in the high sanidine, high Elbaite series, the one of the end member is potassium feldspar, that is KAlSi3O8, and the high Elbaite is NaAlSi3O8. The distinct parameters of alpha, beta and gamma in high sanidine is 1.518 to 1.521 angstrom, whereas in sanidine it becomes 1.518 to 1.524. The beta in high sanidine is 1.523 to 1.525, whereas in sanidine it is 1.522 to 1.524. The gamma is 1.524 to 1.526 in high sanidine, and it is 1.522 to 1.530 in the sanidine. The corresponding anorthoclase, which corresponds to high sanidine, these values range for alpha between 1.524 to 1.526, for beta 1.529 to 1.532, and for gamma 1.53 to 1.534. The lower temperature, that is the high Elbaite of this series, has the alpha value between 1.5 to 6, or it is almost fixed at 1.5 to 6. There is much less variation in high Elbaite in beta also, where it is between 1.532 to 1.533, and similarly gamma is relatively less variable between 1.534 to 1.541. Now, high sanidine in plane polarized light we can identify in volcanic rocks as euhedral crystals in some cases. Otherwise, all the feldspars have optical property of low birefringence, and they are not very easy to distinguish because their crystallography is not apparent in the thin section. The second series of the alkali feldspar is the Orthoclase low Elbaite series, and it is in consonance or similar to the high sanidine Elbaite series. Now, in case of Orthoclase low Elbaite series, it is at slightly lower temperature, and the values of alpha, beta and gamma vary, are lower than that present for the high sanidine high Elbaite series. So, the alpha is 1.518 to 1.520 for Orthoclase, whereas it is for low Elbaite 1.527 to 1.530. For Orthoclase beta is 1.522 to 1.524, whereas it is 1.531 to 1.533 for low Elbaite. Similarly, for gamma 1.522 to 1.525 angstrom is the value for Orthoclase, and 1.536 to 1.540 is the value for Elbaite. So, this is the second series of alkali feldspars. There is one more series which is the relatively low temperature series of alkali feldspar, which is known as the microcline low Elbaite series. Both are triclinic crystals in this case. In case of microclean low Elbaite, the crystallographic parameters vary in this fashion, that is the alpha varies between 1.5416 to 1.516, and the for low Elbaite the values are similar to what we see in the Orthoclase Elbaite series. For beta in monoclinic Orthoclase is 1.518 to 1.519 and gamma is 1.521 to 1.522. So, these are the types of alkali feldspars which are present. Their solid solutions in each series is different and that is reflected in their crystallographic parameters also. Now, we will talk about the Plagioclase feldspar, which is represented by the lower end of this diagram. As we see, if you look at the formula of Elbaite and the formula of anorthite, we see that for a solid solution between the two, the substitution is not very simple. That is, there is no simple replacement of sodium by calcium or calcium by sodium. Why this is so is because the sodium is has single positive charge, whereas calcium has two positive charge. So, therefore, when this substitution takes place, there is a coupled substitution of this nature, that is a sodium replaced by calcium, since there is one positive charge. So, here we have silicon on this side which has 4 positive charge. This needs to be balanced by total of 5 positive charge on this side. So, therefore, for each sodium replaced by calcium, a silicon has to be replaced by aluminum. As you can see, the charges on two sides are both equal now. So, therefore, this substitution is little complicated compared to the substitution which is there within alkali feldspars which have similar charges. Now, pure anorthite cannot support a highly ordered structure below its melting point, just below its melting point. Therefore, and also as you can see that the ratio of Al and Si is similar, 1:1. So, therefore, there is significant substitution. Now, compare this with the situation in alkali feldspar where the ratio of aluminum to silicon is 1:3. So, 25%, 75%, where here it is 50%, 50%. So, there is a significant amount of substitution and disordering seen in Plagioclase substitution. Now, the Plagioclase, this is very well explained when there is a melt crystallization under equilibrium condition, that is a Plagioclase which is crystallizing slowly through a melt will first make a calcium rich Plagioclase. As the melt cools down and if the cooling is slow enough, there will be a coupled substitution with increasing amount of sodium entering into the structure, and one will have any amount of any of these variant present in the finally solidified rock, and that will be controlled dominantly by temperature. So, therefore, it is also in one way it can be used as a thermometer or a geothermometer to interpret the temperature of formation of rock. Now, the feldspars, this behavior is not supported when the feldspars are forming in solid state in metamorphic rock. That is, the 100% solid solution is not observed in them. Because of that, when these feldspars are changing, that is a sodium feldspar is becoming increasingly calcic feldspar, with increasing temperature during metamorphism, there is normally a 10 mole% gap where the oligoclase composition to Elbaite composition there is a jump, and that is known as peristerite gap. We can look at the different structural forms, because when this substitution is taking place, the crystallography is controlling or different crystallography results. We can look at that illustrated in a diagram. As I explained, the structural state of feldspar is a temperature dependent phenomena. So, we can look at this in a temperature versus mole percent diagram for feldspar, within which you can see that there is a domain marked of melting temperature of feldspar is shown and different structural states of feldspar are explained. In this diagram, as we see, there are two positively sloped lines which segregate C2 by M, that is the monoclinic structure, towards high temperature side. As I mentioned earlier, the high temperature means more disordered feldspar, and this slope intersects the temperature axis as 1000 degree centigrade. So, this normally represents higher temperature, as we also see that the melting axis intersects this. So, there is only a small area where the solid phase and the C2 by M structure is stable. It is stable only at very high temperature. Then we have C1 and 2 structures which segregate increasingly lower temperature feldspars. Now, in this, which is a diagram of the Plagioclase feldspar, if you see in the lower part, there are certain areas which are indicated by irregular lines. These represent, because of the differences between sodium and potassium ionic radii, sodium and calcium ionic radii, sorry, the calcium is a smaller cation, sodium is a larger cation. At lower temperatures, fine exsolutions take place, that is, the phases separate out as solid phases and you see a antiperthite or perthite formed, and perthite in case of alkali feldspar as being host and antiperthite in case of dominantly plagioclase being the host. And you see lot of intergrowth which are not resolvable by ordinary optical microscopes, etc., and one requires normally the transmission electron microscopy or high resolution SEM to distinguish these intergrowths. It is important to see that feldspar represent one of the most important mineral present on this moon. Okay, today we have learned about one group of minerals within the Tektosilicates or the framework silicates. You see that the feldspars constitute an important group of minerals. Now, these we have seen are numerous. These crystallize in monoclinic and triclinic systems, and it is a function of temperature. We have also seen that the substitutions are temperature controlled and they control the symmetry. We have seen that the substitution of especially the tetrahedral side describes the order disorder in the feldspars. Thank you.